A month ago, I made a video about the problems with probability, so it's time to try to figure out how to approach it. The natural place to start with probability is with particular outcomes out of total outcomes. The odds of rolling a 6 on a fair 6-sided dice is 1/6. We want one of the faces to be rolled out of these 6 possible rolls. Total probability is 1, and there is an equal chance for each side. Simple enough, for now. If we roll 2 dice, we can make a table of the outcomes, and voila! 36 possibilities. It's as easy as 6 times 6 to count the total outcomes. So now we get to particular outcomes. If we want sums, we can get numbers between 2 and 12, but they don't appear with the same probability. Fortunately, we can simply count up how many times a sum appears using that each pairing has the same probability of showing up. With this, probability becomes a game of combinatorics. Of course, combinatorics is hosted by its own set of challenges, but we won't go there today. However, we've established a solid foundation for probability. When you're looking for a probability, break your outcomes into equal outcomes and count them. And it would be nice if this is all there was to probability. Of course, not every probability problem is just about rolling pairs of dice and noticing that some sums are more likely than others because there are more ways to get them. However, starting with this simple system gives us variations into other forms of probability. One modification is to have continuous variables. Instead of discrete numbers that come in the form of rolls of dice, what if you and your friend show up to a coffee shop for 15 minutes at some time between 8 and 9? What are the chances you meet? Now, you could split the time into minutes and count with the 60 minute by 60 minute grid to count 3,600 possible combinations, but you could also cut the problem into the 3,600 seconds, or 3,600,000 milliseconds. Square those for even more combinations. But wait, do we even need to list these out in a table? What if we just did without them? Here, we can replace the table with a graph, where when you go to the coffee shop is the time on the x-axis, and when your friend goes is on the y-axis. 15 minutes is a quarter of an hour, so if the line y equals x represents you both arriving at the same time, you can show up within 15 minutes of each other, giving bounds for how long you will each stay at the coffee shop. Rather than a counting problem, we have a geometry problem of calculating area where you and your friend meet out of the total area. Fundamentally, it's the same particular out of total idea. These types of problems ultimately come down to determining how much a particular outcome occurs compared to a total outcome. Ultimately, this type of probability is about combinations. I mean, for most times you arrive to the coffee shop, there's a stable 30-minute window for your friend to show up. However, closer to the ends, this window shrinks down to 15 minutes. The combinatorial aspect just becomes about comparing the weight of all possibilities and trying to properly average it out, which we can use geometry to visualize and solve. With this, we can take your friend out of the problem completely and just take how long of a window is left. There's a 1/2 chance there's a 30-minute window, and for the other half, it's just between 15 and 30. This is a weighted average problem to calculate particular, and then we divide by the total 60 minutes. This brings us to another problem in probability. Not everything is fair. I mean, just in the case of the previous problem, not every time leads to the same outcome. Let's go back to the case of rolling 2 dice. What if we add a third dice? If we don't want to add another dimension and turn this into a cube, a natural idea would be to put the 2 dice possibilities together onto one of our axes. However, we only have values between 2 and 12, not the same 36 we had represented before. We can forget about that for now and create our grid anyways, but then we have to add weights again. 3 is twice as likely as 2, 4 is thrice as likely, and so on. We can represent this by splitting the columns based on how often they show up. More generally, however, we can just allocate space along the axis proportional to how likely a result is to show up. With this, we have brought the balance and fairness back to our portrayal of these probabilities. Once again, we can blend this fix into a more continuous problem, like maybe there's an ice cream shop with 4 flavors. The probabilities can be a little more varied, like maybe 44% of people get vanilla, 36% get chocolate, 13% get coffee, and 7% get strawberry. What we want to do is give space proportional to how frequently it's chosen, and if there are toppings that also come in different probabilities, we want to similarly divide across by frequency. And to get a specific result, all we do is multiply the probabilities to get area, and then out of 1 is just the probability. Seems simple enough, right? Multiply probabilities to get areas and make sure different outcomes have their proper weight. In the end, it's about the particular outcome out of total outcome, and we just need to be careful to properly count and make sure probabilities weigh out. Well, that just leaves the question of what if different flavors favor specific toppings? A question of independence that I might get to another day.